Welcome to our presentation, From Legacy App to Platform as a Service. In this presentation, we will provide you with an understanding of Docker containers, Kubernetes, and PaaS systems that will help you prepare your legacy system so it can operate in a PaaS environment. Your legacy app was probably designed to run in a traditional bare metal environment. In this environment, the application was given ownership of a physical server that was sized to support the highest load expected. The data center housed at least one server for every major application. The next phase was server virtualization. Virtualization counted on the fact that servers usually average around 30% utilization and only peak for a short time each day. This allowed IT to increase the application density to 3 or 4 applications on a single physical server. The density increased, but the logical architecture didn't. The virtual topography mimicked the physical topography. Docker does not just mimic the old architecture. We want to break our application into small components which can easily start, stop, and horizontally scale as needed. We also introduce new types of containers like volumes, sidecars, and operators. 10 traditional applications may easily become 500 containers. But the key benefit is that the containers use resources so efficiently that the application density may rise to 40 or 50 containers on a single physical server. Let's take a look at this resource efficiency. I'm giving this demo on a small personal laptop. Here I am running Oracle Enterprise Edition. As we know, Oracle usually requires the largest servers in the data center, but I'm able to run it in a container on my laptop. It might surprise you to learn that I'm not just running one copy of Oracle, but I'm running 5 copies, along with 2 copies of Tomcat and 3 copies of Nginx, and the total CPU consumption is a fraction of a single core. However, if one instance does require more horsepower to process a query, it will receive it. In this example, Oracle DB1 receives more than 1 core to handle the 4-second query. What Docker accomplishes is impressive but not practical at scale. We can't have system engineers starting and stopping containers all day, so Kubernetes enters the picture. Kubernetes was invented by Google to manage all their Docker containers. The servers designated to run your containers are called nodes. You could have a few nodes or 10,000 nodes running 50,000 containers. Kubernetes also provides a scheduler to make sure you have the right types and quantity of containers at any one time, an API service so you can talk to Kubernetes and the containers, a repository to store the state of the containers, and a controller to manage it all. Kubernetes doesn't just run a container, but requires a YAML file that describes the containers, the storage volumes, the virtual networking, and any related services like load balancers. When you deploy the YAML file, the environment is built. The deployment, the services, the pods, which could be 1 or more containers, and the ports are open. In this example, our deployment has created 7 pods, 1 database tier, 1 web tier, and 5 replicas of the application. A key benefit of Kubernetes is the quality of service it provides. If we attempt to delete a pod, in this case the one ending in RxLJ4, the scheduler will kick in. As you can see, it has already created a replacement pod, so the count remains at 5 replicas. Of course, we can change the replication count at any time. In the first example, we reduce the replica count to 2. In the second example, we change the configuration to auto-scaling so the replicas can range between 2 and 5 depending upon CPU utilization. The key point I would like to make is that Kubernetes picks up where we left off with Docker. It gives us a way to run production with high fidelity. But what about the development and test environments? That's where PaaS comes in. PaaS creates a platform where developers and testers can control containers and their environment. The Red Hat OpenShift architecture can be a bit daunting at first, but it simply wraps what we already have seen. Docker is an underlying technology, as is Kubernetes. But it also introduces self-service to the project teams, as well as build automation tools. OpenShift has too much to demonstrate in such a short presentation, but I would like to focus on a few critical features. First, we have a project, and a project defaults the virtual network so that any application in the project can talk to each other, but applications outside an individual project cannot talk to each other. Also, a project comes with a quota, which allows the project team to use their resources in any way they wish as long as they don't exceed the quota. There is a service catalog, which is loaded with all the approved tools, databases, and applications. It is a catalog of YAML files, which a project team can select and run, as we are doing with MySQL. It is that easy for a project team to create a MySQL database. As you may have noticed on the screen, there are several Kubernetes features that are conveniently presented to the project team in an easy graphic form. For example, scaling up and down requires a click on the arrows. Also, service routes are generated for you. The preferred approach to deploying is what Red Hat calls S2I, source to image. I launch a base image, PHP in this case, and I provide a Git location. The system installs the code from the Git repository into a base image, and in a minute we have a working instance. As shown on the screen, the PaaS platform has pulled the base image from the container repository, pulled the code from Git and loaded it into the base image, performed the build, and it will deploy and expose the new instance. With S2I deployments, it is easy to automate through webhooks. In this example, an instance already exists. When I push new code to Git, webhook triggers a rebuild in OpenShift automatically. For dev and test instances, the developers will trigger the rebuild by their own actions without having to engage operations. So with that quick overview of Docker, Kubernetes, and PaaS, let's prepare our legacy application for the new environment. This will require 2 steps. First, we must theme the application. This means finding all the points in an application where it can be decomposed into subcomponents without breaking the application. We want to create application components that can exist on their own and ideally be defined in a Git repository. Ultimately, we will build a YAML file that defines how all these components work together. Second, we want to find the object inside a container that must persist between launches. A container is considered ephemeral. If I kill a container, it must relaunch the container from the original image. Then any data previously written inside the container will be lost. Let's look at our Nginx container from earlier. There are a few temp files that can probably stay inside the container. The pip file is also only relevant to this container and can stay. The HTML files probably need to come out and be put in a volume. That way, when we launch a new Nginx container, it will be linked with our volume and will be ready to start serving up our web pages. That was easy, but let's look at Oracle. There are hundreds and hundreds of files changing inside the container. It may take a few days to analyze all these files, and we may even have to relocate some of them so the persistent objects can be mapped to a volume. The process for containerizing a legacy application isn't hard for someone that knows the application. If a legacy application can run in Linux, it can run in a container, but it must be themed and persistent objects must be mapped. We can then build a YAML file to define the environment, add webhooks to the deployment, and we have a fully automated environment for our legacy application. Thank you for watching our presentation. If you would like any additional information, please contact us using the information displayed on the screen.